In video 5 on work, we're going to look at how to break up a problem that involves either a complex path or a variable force. The equation that we gave you before has to use infinitesimal displacements because either the magnitude of the force or the angle between the force and displacement vector may change as the object moves toward its path. If this doesn't happen, if it's a simple problem where the force is aligned directly with the displacement vector, you get the simplistic type formula called work is force times distance. This is often what's given in IPC courses or lower level physics courses. Then we have the one where the force doesn't quite like along the displacement and we had this angle and we did the dot product. But what if we had a problem like here where we go between A and B, and let's assume for a minute that the force is constant through the whole problem and points like this. Even though that's the case, as we go along we're going to find that the amount of work done over any part of the path is different at different places. Let me show you that. Let's start by considering a small part of the path right here. Now if that's the displacement vector and we have our force vector, then the amount of work depends on this length, this displacement, and this angle here, theta. But if you choose a different part of the path, say the next part of the path right here, now my displacement vector looks like this, and my force vector looks like that, and the angle has changed between those two. From the last one where we showed you how to handle the complicated ball path, what you see is that the way to work any of these problems is simply to break up this path in a bunch of smaller paths and to calculate the amount of work done in each little piece. Along each path, say this path here, there is a vector for the displacement and there is a vector for the force. You take the dot product, calculate the work done. You do this for each part of the path. So for instance here, there's the force, but the displacement vector is like this. Over here the displacement vector is like this, and the force is almost 180 degrees out of alignment with it. So this is going to be producing negative work, whereas over here you had positive work. You do this at each point and you sum it up. Now this may seem extremely tedious, and in fact it would be. I might have to do several hundred, but we could use, for instance, a spreadsheet or other method like a computer to do this sort of calculation for us, and this is what's actually normally done in computer methods. So what we do is just calculate the work at each small displacement and sum up those works. Now you can also have the case where the force is changing, so instead of just the force arrow always pointing horizontally, the force arrow could be moving around. That makes it even more complicated. Now, even in one-dimensional problems, like I said, you could have another issue that comes about. Let's say that you have a path along the x-axis between A and B. So here, the path is not difficult, and we might even have a force that points in the same direction. But at one point, the force might be this long, whereas at this point the force might only be that long. So the works could change just because the force varies. An example of that would be as if the force happened to be x I hat. So as you walked along the x-axis, the force is going to get bigger the bigger your value of x. This is going to change again how you do that type of calculation. Now what you can do with that is that if you take fx and you dot it with delta x I hat to calculate the work in this case, you're going to get, this is f x delta x. What that says is that it's like a rectangle. It has a height and has some width, delta x. There's delta x, and there's this height, fx. And if the height changes as you go along, then you have a different rectangle. And what you can see as I go along here is that these rectangles are basically filling up the area under the curve if you plot the force against position. So we can approximate the work by simply finding the area under the curve. Area under a force position graph gives work. Now that work can be positive work, or it could be negative work. And it's even possible that the amount of positive work is completely offset by the amount of negative work. Either way, the way to find it would be to just simply draw little triangles and rectangles and figure out how to add it up to find the total amount of work. And in most computer cases, they just do this by splitting the system up into a set of rectangles. Now, there is an analytical method that called integration, and in fact your Logger Pro will do this for you. If you plot the function in Logger Pro and you highlight it and press the integrate button, it will tell you the area under the curve. Alright, let's take a look at some of these type of problems and how you do it. Example: calculate the work done by a force F that has this function F equal yi plus 3j on a particle as it moves from 0, 0 to 1, 2. So there we go, that's 0, 0. And there's another point out here, 1, 2. So this is x equal 1. So this is, and y equals 0. And of course there's a place up here that's 0, 2. And I want to go from this point here, call that A, to this point B, and I want to calculate the work done. So the first one says go from 0, 0 to 1, 0, that is, go along this path. And then follow that by going along this path and calculate that work. I'll call this 1 and this 2. Alright, so the force is equal to yi hat plus 3j hat. The displacement, delta r, this is for path 1, is equal to 1 I hat plus no j hat. F dot delta r is y times 1, which is y, plus 3 times 0, so it's simply y. But along this path here, y is equal to 0. So the work on path 1 is 0. And that's 0 joules. So no work is done along that part of the path. Now, that's just for 1. Now we got to find the work done on the second part of the path, part 2. So in W2, we have the force again, which is yi hat plus 3j hat. But this time we're dotting it. We don't change x, but we change y by 2 units. So W2 is equal to 0 times y plus 3 times 2, 6 joules. Therefore, W is equal to W1 plus W2. This is 0 joules plus 6 joules. The total amount of work is 6 joules. So, following the path from here to there, the object's speed increases, and the amount of work done by the force is a total of 6 joules, all of it done on the vertical path. We'll finish this example and on the next video.